Hi everybody, welcome to another video in Calculus 3, section 16.7, chain of variables in multivariable integral. So as usual, in Calculus 3 I try to make a connection to what did we do in Cal 1, and in this case it's no exception. So the chain of variable, the equivalent to that is the substitution rule. So let's say we have just a simple one, integral of 5x plus 1 dx. Of course there may be the limits too, but let's not focus on that. Now we let u equal to 5x plus 1 be here. And then we will solve for the x. So to get to the x, we will take the derivative. And then I multiply the x. So du is equal to 5 dx. And so for dx, so divide by 5. So du over 5 is dx. So this is the standard substitution. We have u and we have dx. And now substitute back into our problem. We have square root of 5x plus 1 is going to be u, and dx is du over 5. And of course we take 5 outside and integrate. But now let's focus on this. Instead of write like that, I can write square root of u divide by 5. I'm going to write 1/5 and then du. So other than the substitution here from that into u, we have the 1/5 and then du, right? So what is 1/5? Now let's focus on that. We have the derivative of u with respect to x is 5. This 1/5 is the reciprocal of that. So what happened if we write 5 over 1 and we flip both sides? So we can say dx over du. So we flip that is equal to 1 over 5. Now I substitute 1/5 is dx over du. And then I can cancel out. So that's why I get back to dx. Right. So we'll do similar thing to this, but for multiple integrals. Right, but before that, let's define transformation. A transformation T from a region S to a region R is 1-to-1 on S if T of P equal to T of Q, only if P equal to Q. So we have, let's say, this is the region S, and we transform into T. Transform into R, sorry. The T is the transformation. It says that if we have 2 points P and Q are the same, then we cannot have more than 1. So this is not 1-to-1. So if the endpoint, if the transformation of P and Q are the same, then P and Q have to be the same. If they're not the same, this is not 1-to-1. So if there's something like this, it is not 1-to-1. Right, so that's a transformation. And usually R is the region of X and Y, maybe Z, and S is something else like R, theta, rho, and something else. But usually and X, Y, and Z is in the R region. And we will call S pre-image. And R is the image. Right. Let's look at an example here. Consider the transformation from polar to rectangular. So polar, so we have a transformation T from polar of r theta to rectangular x and y. So this is a transformation from r theta to xy given by that. Find the image. So we don't know the image of this transformation of rectangle from this. If the pre-image is this, so the pre-image is S. We will have the set of r and theta. So let theta be this axis and r be that axis. R go from 0 to 1 and theta go from 0 to pi over 2. Let's say pi over 2 is here. So r between 0 and 1 and theta between 0 and pi over 2. So we have that region in S, and there will be a transformation to what? Right. Since x equal to r cosine, y equal to r sine, that's pretty standard, and r between 0 and 1, meaning that it have to be in a disk radius 1, have to be the unit disk in when r between 0 and 1. And then but the angle is only between 0 and pi over 2, so we only talk about the first quadrant. So in this case, if we draw the image, it's only a quarter of a disk. And that is in XY plane. And this is the image. This is radius 1. Right, so we have pre-image and image. Right. That's easy, right? Like I said, usually R will be X, Y, and Z in the rectangular coordinates, and S is something else. Now what we focus on is that's number. The number that or number or a quantity that allows us to go from the X originally into a different differentials, in this case du. And that's what we call the Jacobian. So when we have a transformation from uv to x and y, then the Jacobian determinant, or just Jacobian, is this. So what we have is x and y, two functions corresponding to two rows. So we see the x here, and then two variables u and v corresponding to the row, the column. So the xy corresponding to rows and the columns corresponding to the variable that it depends on. Right, and 2 by 2, so just cross multiply and subtract. That will be easy. So let's look at the first example. Compute the Jacobian of this transformation. Usually when we see this, let's just write out the transformation. This time we go from r and theta to x and y. And the Jacobian is partial derivative of xy with partial derivative of something else. In this case, that's do something else on r and theta. just like this. We're going to need dx over du to go to du. Right. If I spell it out, it will be derivative of x with respect to r, derivative of x with respect to theta. So for x, that's the first row, and then y, second row. First column is with respect to r, second column with respect to theta. Right? Derivative of that, of this, with respect to r is just cosine theta. Derivative of that with respect to theta is negative sine, so negative r sine theta. And then y, derivative of y with respect to r sine theta. And derivative of r sine theta with respect to theta is r cosine theta. Right. 2 by 2 determinant. Multiply this and subtract the other direction. So cosine, r cosine times cosine, we have r cosine square. Subtract r subtract. So this direction is positive, the other direction we subtract, so subtract the negative. R sine times sine give us sine square. So we have r cosine square plus r sine square. Factor it out. We have r cosine square plus sine square, which is 1. So 1 times r is r. So that's why in polar coordinates there is r dr d theta. Now that makes sense. In polar coordinate, dA or dx dy or dy dx is equal to r dr d theta. We have the r here, which is, now we know, is the Jacobian of the transformation. Right, so simple enough. Next, I'll find the Jacobian of this transformation. So the transformation is from uv to xy. So the Jacobian derivative of xy with respect to u and v. We'll spell it out. Derivative of x with respect to u, derivative of x with respect to v, derivative of y with respect to u, derivative of y with respect to v. Now let's put the values. This is x, derivative of x with respect to u, that will be 2, with respect to v is 1. This is y, derivative with respect to u is 1 times v, so it's v, and derivative with respect to v, u times 1, which is u. Cross multiply and subtract, so this will be 2u minus v. That is the Jacobian, or the Jacobian determinant. Right, so simple enough, right? And of course we need that to go from the dx to something else, to the differential of something else. Right. Now we have what we call the chain of variables theorem. In count 1, we just call that substitution rule. Right. So let T be a transformation again from something else to x and y. And okay, on the technical here, and it's 1 to 1, so of that. Now, assume it is 1 to 1, then this is the formula for chain of variable theorem. Originally we have dA could be dx dy or dy dx. And when we go here, that will be dA star is equal to du and dv. Think about it. If we write kind of those cancel out, just like it cancel out here. So go back to x. This case, go back to x and y. By the way, the cancel, it doesn't work like that. But at least, just want to show that. Right, so that's one thing. dA could be dx dy, dy dx, and dA star is du dv or dv du. The reason we have the absolute values here to guarantee that it is positive. Right? Because dA, what it does is it calculates the kind of an area. If you go from this area to the other area, you cannot have anything multiplied by a negative number. So that's why we throw in absolute values. And then the limit here from R is uv to s of s and v. So once again, I can write the transformation t from something else to xy, and that something else is in the space S and xy in the space R. Right, so in that case, instead of x and y, we write that in function of u and v multiplied by Jacobian, and then just that. Simple enough. Right. So let's look at the first example. Evaluate the integral. We have that integral where R is the parallelogram of xy with vertices. So we have this parallelogram 0, 0, 0, and x equal to 0, y equal to 1, x equal to 2, y equal to 4, and then 2 and 5. So we talk about the parallelogram. And this is in xy, so this is R. Have xy coordinates. Now the question is how to find the pre-image in the UV plane and the Jacobian. So we know the transformation here. So that transformation going from u and v to x and y. So UV is the pre-image. Upon here in the pre-image, xy is in the image. Now we need to find the pre-image, and then we have this. So how do we do that? We know those points here in the xy plane, right? Those points in the xy plane. So have xy for all of the points. Right, so how do we find that? So let's say we have x equal to 2u, y is 4u plus v. Now, if x is equal to 2u, can we solve it back in terms of x and y? Right. So, if x equal to 2u, then we solve for it. U equal to 1 half x. Right. And then we will solve for y. Since we have u is equal to 1 half x, I will substitute into this u. So y equal to 4, u is 1 half x plus v. So that cancel out, that is 2x plus v, y equal to 2x plus v. Now if y equal to 2x plus v, then v equal to y minus 2x. So we have v and we have u. So why do we need that? Because we need to find the pre-image. So we have u is equal to 1/2 x and v is equal to y minus 2x or minus 2x plus y. Now it's easy. We can write u and v in that form. So, can just make a little table like this. Sorry, let's start with xy. U is 1/2 x and v negative 2x plus y. We have the point 0, 0 for xy, 0 and 1, 2 and 4, 2 and 5. Now, u is 1/2 x, so I cut x in half, so we have 0, 0, 1, and 1. That's easy. Now, v is equal to negative 2x plus y, so we still have 0 here. Negative 2 times x plus y. Negative 2 times 2 plus 4, so that's 0. And 2 and 5 make it 1. So, from the xy here, we have uv 0, 0. Let's say 0, 1, and 2. And we have the point 0, 0, 0 and 1, 1 and 0, and 1 and 1. So that is the pre-image. We can say u between 0 and 1, and so is v. That gives us the pre-image. Now, how do we get the Jacobian? Jacobian is always go partial derivative of xy with respect to something else. The variables here in this case is u and v. X with respect to u, x with respect to v, y with respect to u, and y with respect to v. So we have to look not at this, because that actually we look at this, not at this. Xy with respect to u and v. The derivative of x with respect to u is 2, with respect to v 0. The derivative of y with respect to u is 4, with respect to v is 1, and multiply this equal to 2. So the Jacobian is 2. And the transformation mapping this pre-image a square into the parallelogram. That is the transformation T. It's always from something else to x and y. So pre-image, an image, and the transformation itself. So usually there will be three things in the transformation: the pre-image, and then the transformation, and then the image. With three components. Right, that's one way to do it. Another way to do this is solve system of equation. So we can just do like this, like what I'm showing in here, or there's another way to find the points. So I will write out in the matrix form x equal to 2u and y equal to 4u plus v. Instead of writing like that, I will write 2u equal to x, 4u plus v equal to y. So I can write this in the matrix form. Two for u, 0 for v, 4 for u, and 1 for v. And the way I'm doing here is only works if it is a linear function. If I have the square, cube, square root, I cannot do none of that. It only work if we have linear function. And so in the matrix form we can write like this. And then we can put x, y in terms of 0, 0, 0, 1, 2 and 4, 2 and 5 in here. If I put, I just say 2 and 5 here, for instance. Let's say we have the point 2 and 5 for x and y, or 2 and 5 here. We certainly can solve for u and v, right? And the way we do that, I'll use the calculator. Second matrix, go to here, math, and RREF. I believe I showed this one time in class, in one of those videos already. Right, now we just apply to this matrix, alpha, zoom, 2 by 3, and the matrix is 2, 0, 4, and 1. Now, on the last column, we're going to put x and y. Let's say 2 and 5. So we have x equal to 1, y equal to 1. So that's what we have here. Or better yet, we can put everything in the matrix. 2, 0, 4, and 1. For the matrix of u and v. On the other side, we have all the points, right? X equal to 0, y equal to 0, x equal to 0, y equal to 1, x equal to 2, y equal to 4, and x equal to 2, y equal to 5. I'm going to put all that matrix and still RREF. So, second matrix, RREF, alpha, alpha, zoom. Now we have 2 rows, but 6 columns. Alright, so 2, and the last 2 are 2 and 2. Four, 1, 0, 1, 4, and 5. Right. So those numbers, when they're linear, they come from this transformation. So coefficient 2, there's no v, 4u, and 1v. Those are coefficient of u and v. And then this are the point x and y in columns. So x, y, x, y, x, y, x, y. So when we do that, hit enter. As you see, we have the point 0, 0, 0 and 1, 1 and 0, 1 and 1. So certainly we can use a calculator to find those points. But since this is simple enough, we'll do that. So in this problem, what we are given are the image and the transformation. Just need to find the pre-image because we need to write that in the chain of variable theorem. Now, chain of variable theorem. the function in terms of xy dA is equal to, now we change this back to s. The function can be given in terms of u and v, x in terms of u and v, y in terms of u and v, and then the Jacobian absolute values in terms of the other variables u and v. Right, so in this particular case we will have the function is square root of 2x y minus 2x. So we substitute in. So the function is 2x y minus 2x. Just going to copy this. X y minus 2x. Right, so 2x, x is equal to 2u. So I'll substitute in x is 2u. Y is 4u plus v. Subtract 2x, 2x is 2u. Jacobian is 2, absolute values of 2. This case we will write in terms of du and dv. Integral will be from 0 to 1, and from 0 to 1. Alright, let's simplify this. What do we have? 0 to 1 for u and 0 to 1 for v. So that's why we have those limits. So multiply that, give us square root of 4u times 4u minus 4u. So that's just v, right? So we have 4u, cancel 4u, so 4u times v, and then times 2 du dv, right? I can take the 2 outside the integral. Square root of 4uv du dv. Now I'll ask you this. The limits are constant. That's easy, right? So when the limits are constant, if the function is separable, then it's a lot easier to do. We just separate u and v. So in this case, indeed it is separable. So I will do that. Write one more step. We can write square root of 4u times square root of v. Because u and v are positive, so we can write this easily. And then du dv. What remains is just substitute into u and v. I mean, not substitute, but grouping u and v. Group only u, 0 to 1, the function for u, and the for v, so just use the calculator here. Math number 9. From 0 to 1. Square root of 4. I can check the square root of 4 is 2, but it doesn't matter. Right, so we have that. Actually, this should be 1.33333 on the way. The remaining just error. So that's for her. And I will do the same thing. without the 4. So that looks like 2/3. Of course, we can certainly do this by hand too. So that gives us 16/9. So to recap, chain of variable theorem, what do we need? Ideally, we have pre-image, image, and transformation. That will be easy. But usually, we usually are given 2 of those. In this case, we know the transformation and the image. We have to find the pre-image. The way we do that, just solve for u and v, because the image is given. This is what given is image. We will solve for the pre-image. And then we just put in the point and we find that. Or we use the calculator like I showed earlier. So we go from the limit of r. By the way, this kind of difficult to set up the limit. Actually, in this case not, but the limit might be difficult to set up for r, but it is a lot easier to set up for u and v. So we set up the limit for u and v. The function should be in terms of u and v. The price to pay, or what we have to consider, is multiplied by the Jacobian. So we can turn everything into u and v. And that's what we have. So the application of the theorem is not bad. If we have the transformation, the image and pre-image, the theorem should be very simple. Right, on this one, evaluate that integral when r is the square 0, 0. By the way, r again will be of x and y, or the image. Yeah, x and y is the image. The pre-image is something else. And we have the point 0, 0, 1 and -1. Two and 0, and 1 and 1. So we talk about those. This square, that is the this is the image in xy plane. This is image. In order to go to use the chain of variable theorem, we need to know the pre-image, which we are not given. How about transformation? Yeah, not given that either. We don't know that either. So in this case, we only know the image. So what should we do here? Now, set up the limit for the square like this may be a little bit difficult because the boundary, multiple boundary on, doesn't matter where you look at it. If you look in the x direction, there are 2 boundaries on the left, 2 boundaries on the right. And if we look from the bottom to the top, 2 boundary on top, 2 boundary at the bottom. So it looks like we have to split the integral if we want, even if we want to do this. Now, consider this. What is this equation? It goes from 0, 0 and 1, 1. So the equation is y equal to x, right? And what's this equation? Y equal to x, starting from -2, x minus 2. As you said, how did that help? Well, not yet. Try another one. This equation is y equal to 2 minus x. And this equation is y equal to -x. And then you're still asking the same question. How did that help? Right. Now, I will rewrite this. 2 parallel boundary. I will write, instead of y equal to 2 minus x and y equal to -x, I will write by moving x and y to one side. To add x plus x on both sides, we have x plus y equal to 2 and x plus y equal to 0. Now, the other, I will do the same, y equal to x, or y equal to x minus 2. Move everything on one side, subtract x, we have minus x plus y is equal to 0, and minus x plus y equal to negative 2. Or better yet, let's make things positive. Yeah, this I have negative and I don't really like this. It's not wrong, so by the way, just stick to it. It doesn't matter. Move everything on one side, that's what we have. Now, what we see here is actually very nice thing we should consider. X plus y, both of them x plus y, both of them minus x plus y. So why don't we let this equal to u and go from 0 to 2. So with that we have the pre-image, right? And then here we let v and that go from negative 2 to 0. Right? Turned out to be very nice. So we have the boundary for u, boundary for v, where u is equal to x plus y, and v is equal to minus x plus y. So we sort of find the function that link between x, y, and uv. However, this is not the transformation. Remember, the transformation is always from something else back to xy. So what we have here is the inverse transform. It goes from xy back to uv. So this here is actually the inverse transform that goes from xy. Given xy, we find uv. Which is fine though. Remember, in order to find the Jacobian, we have to consider the transformation, not the inverse. Right. So first of all, we know this, which is u and v. So that is the pre-image. So we know the pre-image. We have the inverse transform. We don't have the transform. Right. So what do we do? Of course, from here we can solve for, I will do this in two different ways. The more direct way is just you can solve for x and y, right? So u equal to x plus y. Let's do it the standard way. If just add side by side, u plus v equal to 2y. So y is equal to 1/2 u plus 1/2 v. Similarly, if instead we subtract x minus minus, that 2x, and 1y, y minus y cancel out. So we solve for x is divided by 2, 1/2 u minus 1/2 v. So we have x and y in terms of u and v. So that is the transformation. So t, the transformation, x equal to 1/2 u minus 1/2 v, y equal to 1/2 u plus 1/2 v. And that is the transformation. Now that we have it, we can find the Jacobian. Partial derivative of xy with respect to uv. Yeah. So I said this is a standard way to do it. Certainly not the best way to do it. But derivative of x with respect to u, x with respect to v, y with respect to u, and y with respect to v. Derivative of x with respect to u, 1/2. With respect to v, negative 1/2. With respect to u, 1/2, negative 1/2. Cross multiply, negative 1/4. Sorry, 1/4 plus 1/4 is 1/2. So the Jacobian is equal to 1/2. Right. So we kind of find a lot of things, but most important in the substitution, in the chain variable, we need to know the pre-image because we have to know what the boundary for u and v to evaluate. So we have to do that regardless. And then from that, of course, we have the inverse transform in this case. By the way, we don't have to do all of this just to find the Jacobian, because after all, we don't need the transformation. If we can get the Jacobian somehow, we don't have to do any of this. Because after all, in the chain variable theorem, we have the limits for u and v, and then we know the Jacobian. And then I guess, yeah, you can write that in terms of, it's nice to have the transformation, but we don't have to. Right. So that was nice and all. That's one way to do it. Another way to do this is this. Now if you write u is equal to x plus y, v is equal to minus x plus y. This we said before is the inverse transform. Now instead of finding the Jacobian, we can also write d of uv over d of xy, right? Which is partial derivative of u with respect to x, derivative of u with respect to y, derivative of v with respect to x, derivative of v with respect to y. Derivative of u with respect to x, 1, with respect to 1, y is 1, with respect to x, negative 1, with respect to y is 1. Right, cross multiply and subtract. So it's 2. Now, we have d of uv over d of xy is equal to 2. Why don't we write that 2 over 1? So in that case, if we want to flip, it is 1/2. Exactly what we have here. Like I said, we don't even need to know what is x and y equal to in terms of u and v. We have the Jacobian. That's right. Yeah. So the Jacobian of the inverse transform is the reciprocal of the Jacobian of the transform, right? So because we just switch, and yeah, certainly we can do that. However, the Jacobian one is the one which is xy over something else, right? Now that we have everything, we can substitute back into our problem. It's nice to have x and y, so we can substitute in here. But if we don't have that, yeah, still still okay for this problem. So integral now is square root of x minus y over x plus y plus 1 dA, so that is dx dy. Now the change of variable, and we write in terms of u and v. I ask you, what is x minus y? Right. Yeah, that determined in a minute, but remember we did say that u is x plus y, right? U is equal to x plus y. So x plus y here is u, because that's what we let equal to. Or if we don't want to, let's just say u and then plus 1. And then x minus y. What's that? Well, v is minus x plus y, or v is equal to, or negative v is equal to x minus y. So this is equal to negative v. And then dA is going to be the Jacobian. Absolute values. And then du dv. U going from 0 to 2. And v from negative 2 to 0. Right. So that is, we can use this if we haven't done any transformation. We still be able to do this without the step that we have here, right? We still have this, because that gives us u and that gives us negative v. However, if we have already found the transformation here, then we can just substitute it back in a little longer, but still we have x, which is this 1/2 u minus 1/2 v, subtract y 1/2 u plus 1/2 v, and same thing 1/2 u minus 1/2 v plus 1/2 u minus 1/2 v. That's plus, sorry, plus 1. That's simplified. 1/2 u minus 1/2 u, that cancel, minus and minus, so that's minus v. And that's 1/2 and 1/2 give us a u. And that cancel out, plus 1. So exactly what we have here. Right. So sometimes it's nice to have the transformation, but even without the transformation, without this, we still be able to use the transformation, the chain of variable theorem. Right. Now just evaluate that. And the Jacobian is 1/2. Absolute values of 1/2, which is 1/2, and then limit for u and dv. Right. Now I'll ask you, we have the constant limits. Is the function separable? And then he said, yeah, not yet, but I can certainly bring the 1/2 in front. Split the square root. Now let's group all the u together and all the v together. We have 1/2, and the v that go from -2 to 0. By the way, you might say having a negative inside the square root sounds weird, right? If we have negative inside the square root, that could be imaginary, but it's not. V is negative from -2 to 0. So when we put in here for v, negative of negative is positive. So in fact, we have square root of a positive number. So that's why it should be positive. We should be fine. So that's we group u, and then we group v. So that is v. Now we group u. Sorry. So, if we put in the calculator, I don't think we have anything nice and even here. That might be a problem. Let's go from -2 to 0. Square root of -x. Yeah, that doesn't look friendly at all. Certainly not. So in that case, we have to use substitution. Right, substitution. We use u and v already. Have to use something different than u and v, different than x and y. So how about we use could be w and z. Yeah, how about that? How do we use w and z? So for this integral, let w equal to -v, and I solve for it. Derivative is -1, and I solve for dv is -dw. So that is the general variable. And also we have a little table for v and w. V go from -2 to 0. Substitute in -2 in here. We have w is 2. And substitute 0 in here. We have 0. Right, so those are the change from v to w. Now the other one, let's use z. Z is equal to u plus 1. Derivative is 1. So in that case, dz is dw. Now let's change the limit from u to z. U go from 0 to 2. Plus 2 here we have 3. Put 1 in here we have. Put 0 in here we have 1. So those are the limits. Right. So this is standard substitution problem. So this is equal to 1/2. Now the integral, we're going to use in terms of dw. In terms of w, instead of -2 to 0, it goes from 2 to 0. And the integral -v is w, so square root of w dw. I'm sorry, dv is -dw. -dw. That is w. Or integral for v. For the other one, instead of u, limit for u, we're going to use z 1 and 3. We have 1 over square root of u plus 1. U plus 1 is z, so square root of z. And dz is dw. dz is du, sorry. Yeah, so this is like the substitution we did in calculus 1. Right, now that is w. By the way, let's move the negative in front. That negative. And now the integral from 2 to 0. W 2 to 1/2 dw the other integral from 1 to 3 at the bottom z to the 1/2, move to the top, z to negative 1/2 dz Right, so we have negative 1/2. Integral of w to the 1/2 is w to the 3/2 over 3/2. That goes from 0 to 2 to 0. And then the other integral, z to negative 1/2, integral z to the 1/2 over 1/2. That goes from 1 to 3. We almost have enough space here. Right. Put in 0, we have nothing. Put in 2, we have 2 to the 3/2. Divide by 3/2 is multiplied by the reciprocal. But because when we put the lower limit, this should be subtract negative 2/3. So flip the 2/3, divide by 3/2 is multiplied by 2/3. This is a lower limit, so that's subtract. And then w to the 3/2, so we 2 to the 3/2. And then we have divide by 1/2 is multiplied by 2. And then 3 to the 1/2 minus 1 to the 1/2. Right, just get an estimation. What do we have here? Negative 1/2. Negative 2/3. Two to the 3/2. Times 2 times 3 to the 1/2 minus 1 to the 1/2, or just 1. So I have about 1.38 something. Right, I'm going to post the video here and check the calculation. Right, we're back and we are correct. The negative and negative cancel out, 2 and 2 cancel out. We have 2 and 2. 2 times 2 to the 3/2. Over 3. 2 times 2 to 3/2 over 3. But that 2 cancel out. And then square root of 3 minus 1. So that's what we have. Right. So negative 2 and negative 2 cancel out. There's a 3 at the bottom. 2 to the 3/2 times 2. And square root of 3 minus 1. So that is our answer. Right. So on this problem, they only give us directly the pre-image. I'm sorry, we are only given the image. That's all we are given here. Only know the image. But from the image, we draw and we see, oh, if we have parallel lines, and that would be nice to set up as u and v. So we draw parallel lines, and one of them we let equal to u, the other one is v. So usually if we have parallel lines, let those two should have the same coefficient. So that one of them is u and the other one is v. And we may or may not need to do this. At first I thought I don't have to do this, that's why I only leave this much space. But since we do that, I take a lot more space and we end up with that. So bottom line is we have to write everything in terms of the new variable. Could be u, v, could be r, theta. And now the limits will be in terms of u and v. And the penalty of going from xy to u, v is the Jacobian. So that is the price to pay to go from some variable from xy to something else. Just Jacobian. Right. And so that's what we have. So let's look at another example here. Let R be the region bounded by the first quadrant by this parabola. I'm not even know if we can graph this. We can graph them, but not very nice. Not going to be a very nice graph. Actually, let's just graph all of them. X equal to y squared. We cannot even graph them because the equation is y equal to something, yes, but x equal to, no, it's not good at all. So in this way, this problem, what we are given is not even the pre-image. We just know a bunch of parabola. Now let's just sketch. It might not be accurate at all, but yes, at least we attempt that. X equal to y squared x equal to y squared minus 4. So just 4 units back. I say 4 is here. Sorry, when y equal to 0, x equal to negative 4. Yeah, that's correct. And then x equal to 9 minus y squared. Y squared is this, but x minus y squared, so that would be about here. And then 16, so it's about here. So what we are talking about is this region there. This is in the first quadrant, so we're not talking about this or anywhere else. So we only talk about the one in the first quadrant. I said I might not draw that well, but it is somewhere in that. And the idea here is we don't even need to know what is that. So let's look at all of this equation. So it looks like those two first graphs that open to the right, they kind of parallel, right? So let's write this. X equal to y squared and x equal to y squared minus 4. Can we just move the y squared over, right? Or better yet, let's make things positive this time. Move the x to this side, move the 4 to the other side. So let's say y squared minus x equal to 0 and y squared minus x equal to 4. Yeah, let's write like that for once. So when we have that, we can let u equal to something there. Right, the other two function, x equal to 9 minus y squared, x equal to 16 minus y squared. So let's move the y squared to the other side. So x plus y squared equal to 9, and x plus y squared equal to 16. So the idea here is we try to get some thing common on the left hand side, where the right hand side are just numbers. So with this, we can let u be y squared minus x. Or we say negative x plus y squared, which is the same thing, right? Right. In that case, u will be between 0 and 4. Now from here, we can let v be x plus y squared. In that case, v will be between 9 and 16. Right. So suddenly what we have here, limit for u and v, so which is the pre-image. So in the chain of variable theorem, we certainly can put in the limit for u and v as follows. Now next, what do we need? The Jacobian, right? How do we find the Jacobian? Let's just say we need the Jacobian. Which is derivative of xy with respect to, in this case, u and v. However, because we don't have x and y in terms of u and v, right? So we don't have x, y in terms of u and v. So how do we find that? Instead of do that, what we do is we can say even the Jacobian inverse, but let's not do that. Yeah, we just said, how about we do this in the reverse order of uv with respect to xy. V derivative of u with respect to x with respect to y, derivative of v with respect to x with respect to y. Don't mind the negative. Right, so the Jacobian negative, multiply this negative 2y, and then subtract 2y, so we have negative 4y. So in that case, if we want partial derivative of xy over with respect to uv, what we do is just flip this, right? So what we did is do the reciprocal of it. Alright, now we pretty much have everything. We know the limits, we know that, except what is y squared? If we can solve for x and y in terms of u and v, that would be nice. But let's just take a look at this. We have, so we certainly need to do this. And then we will need to find the function in terms of u and v. So the channel variable, we need the limit for u and v. We need to know the function in terms of u and v, and we need the Jacobian. So those are the three things that we need in the channel variable. So let's just write this again. U is equal to negative x squared plus u y squared. V is x plus y squared. I don't know where the square coming from. Right. Now if we just simply add side by side, x and x cancel out, give us 2y squared. Right? So in that case, what do we have? Y squared is equal to 1/2 u plus v. Right, so that's certainly y squared. Now the change of variable theorem. Right. It's not going to be pretty. Right. The function y squared, that's nice, 1/2 u plus v. Jacobian. What is the Jacobian? Oh, that. Actually, Jacobian. We should take the absolute values because change of variable, we might want to go from an area to an area, and so both of them should be positive. So to ensure that positive, we throw in the absolute values. And that's du dv. U go from 0 to 4, and v from 9 to 16. There's a big problem here. This Jacobian depends on y. By the way, absolute values would get rid of the negative because y, in this case, it is in the first quadrant, so everything should be positive, so we don't need the negative. So that takes care of the absolute values. In fact, I should just give this y squared, right? Now think about this. Originally, we have that is y squared, and the Jacobian is 1 without the absolute values for y, and then we just cancel out, and we just have y over 4. That would be better if we just keep this y squared and substitute that in here, so we can just cancel the y, and that gives us y over 4. That is a lot better. But since already here, 1/4, and y at the bottom It's going to be square root of that. What even worse of all of this is that function is not separable, so the Forbidden theorem will not work here, so that makes things a lot more complicated. Right, so let's just group all the numbers together. 1/2, 1/4, 1/2, but inside the square root. So 1/2, 1/4, square root of 1/2, and then we have, yeah, this is much better if we just leave the y square here. Right, that cancel out and simplify all of this. Square root of 1/2, can I write this as one over square root of 2. Divide fraction is multiply reciprocal, so this was 1/8 multiply reciprocal, so we flip this, and the function cancel the square root, so this you can say as square root square. I get back to u plus v, right? So that cancel out square with that, so we just end up with square root of u plus v du dv. Take the constant outside, square root of 2 over 8, 9 over 16, 0 to 4, square root of u plus v du dv. Right, if this is Forbidden theorem, that would be a lot better, but it's not. The function is not separable, so we just have to integrate. Substitution. Yeah, I should have seen this before, so I take advantage of that space. Right, substitution. Let w equal to the u plus v. So derivative of w with respect to u is 1. So w dw is equal to du. Right, and yeah, worry about the change of the limits later. Square root of 2 over 8, 9 to 16, 0 to 4. I do not change the limit here, so I would say u equal to 0 to u equal to 4 still. And we still have u equal to 0 to u equal to 4. We don't change the limit yet. Square root of u plus v is w. dw is equal to du. And then dv. So I have square root of 2 over 8, 9 over 16, square root of w, integral of that, I'll skip a step, say w to the 3/2 over 3/2. Integral going from u equal to 0 to u equal to 4 dv. but I have to write this as W as U plus V first. Before I substitute 0 and 4. Oh, sorry about put now space here. So divide by 3/2 is multiply the reciprocal. So square root of 2 over 8 divided by 3/2 multiplied by 2/3. Nine over 16. Then we're going to put 4 in here. And then we put 0 in here. Zero in for U. V on the outside. Right. So that's complicated already. So let me just get an evaluation here. Just get an approximation. So we have square root of 2 times 2, that on the top, divided by 8 times 3, 24 at the bottom. And then we have an integral. 1 from 9 to 16. Four plus x to the 3/2. Just minus x to the 3/2. Right. I said that's because another substitution, but approximately we have 18.78. Right. But the point here, of course, is I should put another function here to make things a lot easier to evaluate. Instead of y squared, here I should just put negative x plus y squared in here. That will be just u, will be a lot easier to do. I take that back. It may not be easy to do because we still have y here. So if I want things to be a little more easy, a little bit easier to do, I should put y cubed here. Things will make a lot easier. Because here we have the function y squared, the Jacobian is 1 over 4y. That cancels out, we have y, which end up being the square root, which is not very nice at all. But if we make it y cubed, then y cubed cancel out here, we have 1/4 y squared, which is just 1/2 u plus v. Still not separable, but at least we don't have to deal with the square root. The square root makes things more complicated. But the bottom line is, when we are look at this equation, trying to find something similar, when we move everything on one side and we have constant on the other side, that gives us the transformation, the inverse transformation along with the limits. The pre-image is very important, that's the boundary, that's the limit for the integral. And the Jacobian, we might not be able to find that directly, but we can do the inverse of that. And then we'll just flip and that. Usually we should have an easier function to deal with. This problem is a little more complicated. But the answer, the function has to be in terms of u and v. And we evaluate that, which is equal to, okay, that. Right. So those are chain variables with 2 variables. Now if we have 3 variables, and this still count the same way. So we still have the transformation of something else to xyz, and the Jacobian is partial derivative of xyz with respect to u, v, w. X for the first row, y second, z the last row. The columns with respect to the variable u, v, and w. So it's not big deal. So that is the Jacobian. So let's just derive the two Jacobian for the spherical and cylindrical coordinate. So for cylindrical coordinate, the change for that is x equal to r cosine, y is r sine, and z is still z. Right. So the Jacobian derivative of x, y, and z with respect to r, theta, and z. Yeah, even though we have the same z, but that's perfectly fine there. So, derivative of x with respect to u, v, and w. So derivative of x with respect to r, theta, and z. With respect to r, we have cosine. With respect to theta, we have negative sine, which gives us negative r sine theta. With respect to z, there's no z there, derivative would be 0. So that is derivative of x with respect to r, theta, and z. Now look at y. Derivative of y with respect to r. Theta, and again there's no z, and then derivative of z with respect to r, there's none there. With respect to theta, there's none. With respect to z, it's 1. So this, of course, 3 by 3 determinant we can evaluate like we did before. However, remember when we use this in the cross product, we're going to pick a row and a column to evaluate. We certainly can just pick out the first row, but it would be better if we pick out the last row or the last column. So let's evaluate based on the last column here, last row here. So if we evaluate based on the last row, we have 0. After that, we'll cover the row and column containing that one. So the submatrix is what left. I'm going to put here. And then the next one, and the submatrix, and then the last one, the submatrix. So we have 1. So it's much smaller. Cosine, negative r sine, and then sine, r cosine. Right. Determinant. Just there's a line on the back. Sorry about that. Right. Now, that's nice and all, but notice there is the sign chart too. a sign chart is like the chessboard, start from positive and alternating every direction. So it's going to be positive, negative, and positive. Good thing here is 0 times anything is 0, so those two cancel out. We're only left with the last one. So let's write that again. 1 times, go over the row and the column containing 1. We have cosine, negative r sine, sine, and r cosine. Cross multiply and subtract r cosine square plus r sine square. Cosine square plus sine square is 1. Which is 1. So this is equal to r. So that's why in spherical coordinates, in cylindrical coordinates, we have r, dr, d theta. Right. So it's not that bad. Something. The next one will be bad because we have 3 variables and they're not equal to 0 like this. Right. So for spherical coordinates, I should move everything up and to have more space here. Right, x equal to r cosine theta in cylindrical, but we have an extra so we can r is equal to opposite to the phi angle. So that equal to rho sine phi cosine theta. Y equal to r sine theta. So rho sine theta, rho sine phi cosine theta. Z is adjacent to it, so rho adjacent. Right, now let's put in the Jacobian. Get a sense now we have to write very small here because we might not have enough space. The 3 by 3 determinant could be complicated. X, Y, Z. The variable here will be rho, phi, and theta. Right. Derivative of x that function with respect to rho, phi, and theta. With respect to rho, there will be just sine and cosine. With respect to rho, it's going to be, with respect to phi, is rho. Derivative of sine is cosine, and that's cosine. And the last one, with respect to theta, is negative rho sine phi. Derivative of cosine is negative sine. That's why that's negative. Next, derivative of that function, y with respect to rho, phi, and theta. With respect to rho, with respect to phi, derivative of sine is cosine. if I write this correctly. So I have cosine, derivative of sine, and then still sine theta, and then derivative of this with respect to theta. Is cosine. Finally, the last one with respect to rho is cosine. With respect to theta, with respect to phi, is negative sine, and with respect to theta is 0. Right. Once again, we evaluate based on the last row because there's a 0 there. It's a bit convenient. Right. Now, we're going to write out the component cosine theta cosine phi then cover the row and the column. Right, row cosine cosine sine sine row cosine sine row sine cosine. Right, that with respect to this one. Next, with respect to the negative, row sine of phi. Remember, on the sign chart, this one will carry the negative sign. So cover that up. So I have sine cosine negative row sine 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 and sine row sine and cosine. And the last one is 0. We don't have anything, so that's all we have. Now cosine row here, cosine of phi here. Now multiply this cosine square sine cosine, so we have row square sine cosine and then cosine square. The other direction, negative negative, so that's a plus row square. We have sine cosine here, right? Sine cosine and then sine square. Then minus minus, that's a plus row sine and multiply this cosine square sine square and cosine square. minus negative, so that's the plus sine square and sine times sine. Right, actually this simplifies a lot. Now look at the common factor here. If we factor it out, we have cosine plus sine square, which is 1. So that's simplified. By factor those two out, we have sine cosine. Since I don't want to skip a step, I have to write this on a separate more space here. Right. And then factor that out. Then we have sine cosine, sine square plus cosine square, which is 1. And then we also can factor out this. And then once again cosine square plus sine square. So this is not that bad. And sometimes when I was a student, I prefer seeing a problem like this than to do something that I don't know the answer. We know the answer for this one is rho square sine phi, right? This equal to 1. So we end up being rho square sine and then cosine square. And then rho square sine times sine square sine cube. But I'm not multiplying it out, just leave it. So once again, factor this out. And cosine square plus sine square. That is 1. So that's what we end up with, the Jacobian of spherical corners. Going from rectangular to spherical corners. That's what we have of that. Yeah, so it's not that bad. The idea is derivative with respect to xyz of xyz with respect to the new variables. This problem is just a bit tedious, but certainly doable. Right. Right. Now we have a general variable theorem in 3 dimensions. So it's nothing different than what we have before. It's just that we have 3 variables, x, y, z. Now we're going to write that in terms of u, v, w, and then the Jacobian, and the v star here is going to be u, v, and w. And the dv here originally is dx, dy, dz, or dy, dx, dz in any order. Right. Now use the chain variable to set up the triple integral. Okay, we might not be able to evaluate, depends on what function we have. Right, so we have that. So let's just put things together. All right. Actually, just set up. Use the chain variable to set up the triple integral to evaluate. So we not evaluate, but just set up the integral. So much better. So when we look at all of this, just like what we had before, look for something that when we move to one side, there's something similar. Look at those two. If we move on one side, then we have y minus x, the other side constant, which is good. So group those two together, that's one variable. Next, for this two, move the z x on one side, we have constant to the other side, which is good. That's another variable. And this two, so z is equal to 0 to 4, so that's certainly just z, which is good. Right, so let's start. Right, so y equal to x and y equal to x plus 2. Let's keep positive on the left hand side, so move the x over y minus x equal to 0, y minus x equal to 2. So this one, it would be wise if we let u be y minus x and u will be between 0 and 2. That's convenient. Next is z equal to x, z equal to x plus 3. So move things around. Z minus x equal to 0, z minus x equal to 3. So we have those the same thing on the left hand side, the right hand side is constant. So in that case we will let v equal to z minus x, and z goes from 0 to 3. Finally we have z equal to 0 and z equal to 4. So in that case we can just let w equal to z, and w between 0 and 4. So this will be the pre-image. Where we set up the limits. And those functions help us to find the Jacobian. Right, let's find the Jacobian. Derivative of x, y, z with respect to u, v, w. We won't be able to do this because we don't have x, y, z in terms of u, v, w. We have the opposite to that. So instead of do that, we do partial derivative of u, v, w over derivative of x, y, z. Once we have after that, we just flip it, and then we have the Jacobian of the one we want. So now we get the idea of this kind of problem. When we look at this, we're trying to find some common function group 2 by 2. So we have the variables, and then we have the transformation, the inverse transform. Right, so derivative of u with respect to x, I'm just using the subscript to save space. U with respect to y, u with respect to z, v with respect to x, y, and z, w with respect to x, y, and z. Right, derivative of u with respect to x, with respect to y, with respect to z. Derivative of v with respect to x, with respect to y, with respect to z. Derivative of w with respect to x, with respect to y, with respect to Yeah, obviously we make a mistake here. Otherwise, if we have a row of column of 0, determinant is equal to 0. So where the mistake was? Oh, I think it's here. Once again, derivative of u with respect to x, -1, with respect to y, 1, with respect to z, 0. Derivative of z with respect to x, with respect to y, with respect to z. W with respect to x, y, z. That's good. That's good. So determinant, you can pick any row, any column. This one is simple enough. Actually, I'm going to take the last row because everything else 0. So positive, negative, positive, negative, positive. So the one sitting on the plus sign on the sign chart. Yeah. So the last one is positive. So just have positive. Cover the row and the column containing that entry. Multiply here, that's 0, minus, minus. So the determinant is equal to 1, which is convenient. Because if that is 1, we just flip it. So we have the limits, we have 1. Now the only thing left to determine is we need x and z. Just need the function in terms of u and v. So how do we do that? Certainly we know z is equal to w. So we need to write out xz in terms of u, v, and w. So how do we do that? Certainly w is equal to z, that's easy. So that check. But what's x equal to? Notice that u is equal to y minus x, and v is equal to z minus x. Right? So what can we do here? How can we get x from this? Right. We cannot eliminate y or z, so the only thing we can do is solve for x and use substitution. I move the x over y minus u. And x equal to z minus v. Just make them equal. So y minus u is equal to z minus v. We can solve for y. So y is equal to what? Move the u over u plus z minus v. Luckily, we do know w is equal to z. So y equal to u plus w minus v. Right? Yeah. So x is Yeah, that's nice, oh, but we don't even need that. Sorry. Just go from here. Z is W, so X equal W minus V. Sorry, that's, we don't even need to go this far. That's directly, we can solve for X in terms of V and W. Right, this one's not that bad because W is equal to Z. So for X equal to Z minus V, W minus V. So that's it. So XZ is equal to X is equal to W minus V, and Z is equal to W. And now ready to substitute back into the integral. Luckily, we don't need to evaluate this. We just need to write the chain of variable. The function is x, z. Right. Equivalent to xz in terms of u, v, and w is this function. So we need to write the function in terms of u, v, or w, right? And then the Jacobian. And then limit u, v, w. The limit should be easy to determine, right? For u, from 0 to 2, there. V 0 to 3, and W 0 to 4, and Jacobian is equal to 1. Absolute value is 1, still 1. So bottom line is we just need to evaluate this integral. U between 0 and 2, V between 0 and 3, and W between 0 and 4. Right. So that is a lot easier to do than the original one. Right. We only need to set up the integral. We don't need to evaluate. So that's what we have. Right. So that's what we have, the chain of variable. So we need to determine three things. Let me find those paper first. Okay, to change the variable theorem, we need to write the function in terms of the new variable u and v. Need to have the Jacobian, and they need to know the limits of u and v. The limit of u and v is determined by the pre-image. So usually, when we look at this, we can write something similar. Like this example, where we have the function, then try to move to find something common on the left hand side. So the right hand side will be just limit. So that's exactly what we have here. And with that we have the limits. If we want to find the Jacobian, sometimes we just need to find the reciprocal of that. So we're going to flip, and then we do derivative with respect to u, v first. With respect to xy, derivative of u, v with respect to xy, whatever we have, flip it, and then we have derivative with respect to the correct Jacobian. And finally, we still need to know whatever the function is in terms of the new variable. So, bottom line, need to determine three things. The limits, which is the pre-image, the Jacobian, and then the function have to be written in terms of the new variable. So when we have those three things, we should be able to evaluate it. Yeah. So the concept It's not that complicated. It's just that some of the example here is a bit complicated, especially if it's three variables. That could be complicated. But the concept is not as bad. Once again, the new limits for new variables. In that case, new variables. The function have to be in terms of new variables. And then the Jacobian is what we need to go from one variable to the other. Right. So other than that, I cover everything I want to cover in this section. So, and that also the last section of chapter 16. So this is a little bit long, but chapter 16 only have 7 sections. Each of them is long though. Anyway, thank you for watching.